Here are all the Kepler candidates that were shown on that previous chart, and you notice that the temperatures, this is the temperature of the planet, plotted against its size relative to Earth. So here's the size of Earth, here's the size of Jupiter, here's the size of Neptune, and that's illustrated there. You notice that most of these are hot, and the reason that most of these planetary temperatures are hot is because most of those planets are in very close to their stars. Kepler will discover the planets close to their stars first because it's measuring transits, and of course a planet close to the star will have more transits than a planet far away that's moving slower, and it just takes longer for a transit. It's longer between transits. But some of those planets are indeed down at low temperatures, and those planets in fact are within the so-called habitable zone. So many planetary candidates, and as I say, we expect probably 90% of these will prove to actually be planets, and some are Earth-sized, some are super-Earth-sized, and even the ones that are Jupiter-sized could have moons like Europa and Titan, and those moons could be habitable given that the planet is in this habitable zone, that is where liquid water could exist on the surface of a planet. So let me tell you a little bit about follow-on missions. Once one discovers planets around other stars, of course, you'd like to know what those planets are like. Are they habitable, and can we measure their characteristics? And there were two very ambitious missions that were proposed to do that, and those missions were studied by both ESA and the European Space Agency and by NASA jointly. The missions are called the Terrestrial Planet Finder, and there are two versions of that. One is a coronagraph mission, and that is a mission which would actually use optics to physically block out the light from the central star. The fundamental problem in actually measuring the light from a planet around another star is that the planet is 1 billion times brighter, typically, than the star, is roughly 1 billion times brighter than the planet. It's like trying to detect a firefly next to a lighthouse on a foggy night, because in addition to the brightness difference, there's typically dust around the star. There's dust around our sun, and the light that's reflected from that dust we call the zodiacal light. Other stellar systems have the same thing, and that provides sort of a background glow that makes it even harder to detect the planet. But if you can block out the light from the central star, then in principle you could measure the light from a planet. But it's very difficult to do, and it requires a fairly large, complex astronomical